Hello everyone, I am Mallikarjuna. Welcome to my channel Prakriya Educations. In this module, we shall learn more about matrices. This is 4th out of 6 modules of matrices. In this module, we shall learn about transpose of matrices and its properties, symmetric matrices, skew symmetric matrices, and also solve some problems of NCERT of exercise 3.3. Looking at the first topic, transpose of a matrix. If we chose a matrix A of order 2 cross 3, then we can find the transpose of this matrix by interchanging all the rows and columns. Now, usually the transpose is denoted by A dash or sometimes even this. Now, the transpose is nothing but you are changing the first row of the matrix as the first column of the transpose and the second row into the second column. This is called as the transpose of the matrix. You can also notice that the order is also being exchanged. That is, in this transpose, the order of the matrix will be 3 cross 2. Right? Formally, writing the definition of the transpose of a matrix, if we are given with a matrix A, that is Aij of order m cross n, then the transpose of this matrix, that is A dash or A transpose, is given by we are interchanging the rows and the columns, and hence we get Aj of the order. The order will also be interchanged and hence we get n cross m. This is the formal definition of the transpose of a matrix. Now, we have some properties of transpose of matrix which we state without proof. The first one, A dash whole dash, gives us A back. The second one, a scalar which is multiplied with the matrix A whole transpose, you can take out the scalar and write it as K A dash, where K is nothing but the scalar. And the third one, A plus B whole dash will be equal to A dash plus B dash. You can also apply this for the difference. The fourth one, AB whole dash, gives us B dash into A dash. You can just check out these properties while doing the problems. Now, we shall discuss about the very interesting matrices, symmetric and skew symmetric matrices. Starting with symmetric matrix, take a square matrix A which is equal to Aij of order m cross m. Then this square matrix is said to be a symmetric matrix only if A transpose is equal to A. If this condition is satisfied, then a square matrix can be said as a symmetric matrix. For example, I shall take a matrix A, a square matrix A, and also I'll write the positions of the elements. Here you can notice that, see, this element A12 is equal to the element A21, that is A12 will be equal to A21. Similarly, A13 will be equal to A31 and also A23 will be equal to A32. If at all we are taking the transpose of this matrix, check out for the transpose. You can check that the given matrix A and its transpose are equal to each other, and hence you can conclude that the given matrix A is a symmetric matrix. And hence you can also write this as Aij, that is any element Aij will be equal to Aji for all possible values of I and j. Look at the next matrix, that is skew symmetric matrix. Again take a square matrix A which is equal to Aij of order m cross m. Then this is called a skew symmetric matrix if A transpose is equal to negative of A. And also remember, Aji will be equal to negative of Aij for all possible values of I and j. It may be also the vice versa. Now, another important thing that you have to notice in a skew symmetric matrix is for the diagonal elements, you also remember that the diagonal elements will be of the form A11, A22, A33 and so on, and hence I will be always equal to j for the diagonal elements, and hence we get this expression as Aii is equal to minus of Aii. Shifting this term to the other side, we get which is equal to 0. Adding up this, and hence Aii will be equal to 0, and hence you can conclude that for any skew symmetric matrix, the diagonal elements will always be equal to 0. Now we shall look for a small example. If you are taking an example A, already we know that the diagonal elements are 0. I'll also write the position of the elements. Here you can notice that if I am taking a term A12 and the term A21, A21 will be equal to negative of A12, and also if you are taking two elements A13 and A31, A31 will be negative of A13 will be negative of A31, and taking the element A23 and A32, A32 will be the negative of A23, right? Also, if I am making the transpose of the matrix, then A dash will be equal to, if we are taking negative, that is minus, common out of the matrix, then we'll be having, here you may now notice that A dash will be equal to minus of, this whole matrix is nothing but the A matrix, and hence we have concluded that A dash is equal to the negative of the matrix A. You can also notice the difference between the symmetric and skew symmetric matrix. In the symmetric matrix, if we are folding the matrix along the diagonal elements, these elements which are called as upper diagonal elements and these the lower diagonal elements will be overlapping to each other. And if you are noticing in the skew symmetric matrix, the elements which are upper diagonal elements and the lower diagonal elements, if you are folding the matrix along the diagonal elements, these elements will be overlapping but with the negative sign. We have got two important theorems with respect to symmetric and skew symmetric matrices. Look at the first theorem. It states that for any square matrix A with real number entries, A plus A dash is a symmetric matrix and A minus A dash is a skew symmetric matrix. Looking at the proof now, we shall start with the first half of the statement, that is, let us now consider B is equal to A plus A dash. In order to prove this is a symmetric matrix, we need to take transpose and show that the transpose of B will be equal to B itself. And hence, we shall take transpose on both the sides of the given equation, and hence we get B dash is equal to A plus A dash the whole dash. Using the result of transpose of matrices, we can split the terms and write it as A dash plus A dash the whole dash. Also recall another result, that is A dash whole dash, will be equal to A. Rewriting that, we get A dash plus A. And hence, also remember, when we were doing in the operations of matrices, the addition of matrices will be always commutative, and hence you can exchange the elements and write it as A plus A dash. And hence we have proved that B dash is equal to B, and hence conclude B, which is equal to A plus A dash, is a symmetric matrix. In the similar pattern, we can prove the second half of the theorem, that is, to prove A minus A dash is a skew symmetric matrix. In order to prove that, we take A minus A dash as C and continue using all the properties that we had in the transpose of matrices, and at the end we prove C dash is equal to minus C, and hence conclude that C, which is equal to A minus A dash, is a skew symmetric matrix. Second theorem, it states that any square matrix can be expressed as the sum of symmetric and skew symmetric matrix. The proof follows like this. Take a square matrix A, then a square matrix can be expressed as half into A plus A dash plus half into A minus A dash. If we solve this, you can get back A. Take the first part of the equation, that is half into A plus A dash. We already know that A plus A dash is a symmetric matrix. We have proved that in the theorem 1. Using that, we can prove that half into A plus A dash is also a symmetric. Using the property that we had learnt in the transpose of matrices, you can take out half from the brackets and we'll be left with half into A plus A dash the whole dash. And since we know that A plus A dash the whole dash is equal to A plus A dash, from theorem 1, we can prove that the first part of the equation, that is half into A plus A dash, is a symmetric matrix. In the similar pattern, you can also prove the second part of the statement, that is half into A minus A dash, is a skew symmetric matrix. And hence, we can conclude any square matrix can be expressed as the sum of a symmetric and skew symmetric matrix. We shall solve some problems of exercise 3.3. I have retained the exercise number as well the question number for your reference. The first question, for matrices A and B, verify that AB whole dash is equal to B dash into A dash. Recall that this was one of the property when we were discussing about transpose of a matrix. Now, starting with the problem, we shall first find out A into B, which will be equal to multiplying these two matrices, we get, you can notice that this matrix is of order 3 cross 1 and this is of order 1 cross 3, and we have got the resultant matrix AB of order 3 cross 3. Now, since we need the transpose for the LHS, the LHS is nothing but AB whole transpose, and therefore we get transpose this matrix. We get the LHS as this matrix, and let us take this as equation number 1. Now, going for the RHS, before that we shall first find B dash and A dash. B transpose is nothing but, since we are having only single row, the transpose will be a single column, and the A transpose will be a single row. Now, as per the RHS, we need to find B dash into A dash, multiplying these two matrices. This is of the order 3 cross 1 and 1 cross 3. We need to get a resultant matrix of order 3 cross 3 again. Now we have the RHS. Let us take this as equation number 2. Now check out the equation 1 and equation 2. We notice that both the matrices are equal to each other, and hence from equation 1 and equation 2, LHS is equal to RHS, and hence AB whole dash is equal to B dash into A dash, and hence verified. Look at the next problem. If A is the matrix given, then A plus A dash is equal to the identity matrix I if the value of alpha is. Now, first, as per this equation, we have got A. We shall find out the A transpose. A transpose will be, now having this equation, A plus A dash will be equal to I. Always remember, since A and A dash are both of orders 2 cross 2, I will be also a matrix of order 2 cross 2. Now, adding the matrices A and A dash, we get cos alpha plus cos alpha, we get 2 cos alpha, minus sin alpha plus sin alpha 0 is equal to the identity matrix of order 2, that is 1 0 0 1. Now, since these two matrices are equal matrices, we can compare the elements of these two matrices, and hence 2 cos alpha will be equal to 1, and hence cos alpha is equal to 1 by 2, and therefore recall the angle cos of 60 degree will be equal to 1 by 2, and hence alpha is equal to 60 degree, or changing it to radian measure, alpha will be equal to pi by 3, and hence we have the option as B. Look at the next problem. Express the matrix A as the sum of symmetric and skew symmetric matrix. We have already learned that any square matrix A can be expressed as half into A plus A dash plus half into A minus A dash. We shall now consider the first element as P and the second element as Q. First, always remember, this should be a symmetric matrix, and the second term will be the skew symmetric matrix. Starting with the first element, that is P, your first step, P is equal to half into A plus A dash, half into A matrix plus its transpose. Adding both matrices, we get, now multiplying 1 by 2 to every element of the matrix, we get, this is the matrix P. Now try the transpose of P. We have the matrix which is equal to P, and hence conclude P is equal to P dash, and therefore the matrix P, which is 1 by 2 A plus A dash, is a symmetric matrix. Now consider the second part, that is Q, which is equal to half into A minus A dash. Now half into the matrix A minus its transpose. Subtract these matrices, finding its transpose, and therefore Q dash is equal to negative of Q. Therefore, you can conclude that Q is skew symmetric matrix. The last step, expressing the given matrix, that is A, as the sum of these two matrices. Start with P plus Q. The matrix P that we have got is plus the matrix Q. Adding these two matrices now, hence we can notice that the matrix that we have obtained by adding both P and Q is nothing but the matrix A. Therefore, P plus Q is equal to A, and hence we have expressed the square matrix A as the sum of the symmetric matrix and the skew symmetric matrix. Looking at the next problem, If A, B are symmetric matrices of same order, then AB minus BA is. Now, according to the data, they have given us AB is symmetric matrices, and therefore we can write A will be equal to its transpose and B will be equal to its transpose. Starting with the expression that they have given, that is AB minus BA, to check whether it is a symmetric or a skew symmetric matrix, we have only one condition that we can do, that is to take transpose. Now, we shall take the transpose for AB minus BA and check. Then, simplifying this, according to the property of transpose, we know that A minus B whole transpose will be equal to A transpose minus B transpose, and hence AB whole transpose minus BA whole transpose. And also recall another property, that is AB whole transpose will be equal to B dash into A dash, and hence we can have B dash into A dash minus A dash into B dash. And also by the data we have got A dash is equal to A and B dash is equal to B. Using the data we can change this as B into A minus A into B. This is because we have this by the data, and hence we have AB minus BA the whole transpose is equal to BA minus AB, which is certainly not a symmetric matrix. We shall now take minus common and check. Then we get minus of AB minus BA, and therefore AB minus BA whole transpose is equal to its negative, and therefore it's of the form Q dash is equal to minus Q, and hence you can conclude that the matrix AB minus BA is a skew symmetric matrix, and hence the option is A. Hope you enjoyed the video. Please don't forget to like, share and subscribe. Thank you.